Welcome to the Crazy Hat Chemist. So another video here in Thermochemistry Part 2. So let's get moving. Bam! So today we are talking about Gibbs Free Energy calculation number 1. Alright, bam. We're going to determine the delta G naught for the melting of ice at RT. And what is RT? RT is room temperature. Okay, here's the equation that we're going to look at. We're looking for ice, that's H2O, that's in the solid state, and we're doing a state change. We're going from the solid state to the liquid state. So we are breaking some bonds here, okay, but what kind of bonds are we breaking? We are breaking intermolecular forces, which in this case, specifically for water, we're breaking hydrogen bonds. We're breaking up that crystalline hexagonal structure that's in solid water, which is ice, and then we are breaking a number of hydrogen bonds so that we get liquid water. Now, we're not breaking all the hydrogen bonds because if that were the case, then we would have gaseous water. Okay, we have some information before us that we're going to use. We're going to have the enthalpy term, which is delta H naught for the reaction, and that's positive 6.95 kilojoules for this reaction. So, is this an endothermic or exothermic reaction? So that's what you need to answer for yourself right now. You need to look at that and think, let's see, I'm taking water that's in the solid state going to water in the liquid state, and I have a positive enthalpy term. The sign of this lets you know what the endothermic or exothermic, whatever it is based on the sign, not the numeric value. It doesn't matter that it's 6.95 or 0.695 or 695. What matters is the sign in front of it. And since the sign here is positive for the enthalpy term, this is an endothermic process. All right. Now, we do have a little bit more information yet remaining on this problem. Okay, and that is right here. That is the S naught for the reaction is 28.59 joules per Kelvin. Now, we're going to ask ourselves, well, why is this positive? What makes this value positive? And you're going to go back to looking at this water, that H2O that is in the solid state going to H2O in the liquid state. Okay, and it is positive, so is this becoming more ordered or more disordered? In fact, if you look at some of the previous videos within this unit, I answered that question. And we're going to figure what it is numerically. So we're tying in the conceptual information previously taught in this unit to some mathematical information to back up the conceptual understanding. Hopefully you get that. Okay, since the sign of the entropy is positive, this indicates that the products have more disorder than the reactants. That is, there is more disorder in liquid water than solid water. And hopefully you understood that from looking at the previous lectures of this same unit here. Okay, and that is the solid state is very ordered and the liquid state is more disordered. There are fewer hydrogen bonds between water molecules. Water molecules can have lots of different types of energies. Rotational energy, spinning around. They can have vibrational energy, translational energy, of which is only vibrational energy essentially in solid state. Now, looking at these two values, we want to figure out the Gibbs free energy. Now, that is the key thing here. We're going to look at these and go, well, we got a positive enthalpy and we have a positive entropy term. Since both of them are positive, we really cannot predict the sign of Gibbs free energy. Remember, when the enthalpy and entropy terms are opposite in sign, then we can know for sure what the sign is for Gibbs free energy. But we don't know if any useful work can be done under this circumstance because we actually have two vectors of which are going in opposite directions. That is, they are the same sign, but we need to plug these into the equation to figure out what the overall sign is of this reaction. Okay, and this is the reaction that we're using here, which is Gibbs free energy, which is delta G naught is equal to delta H naught minus T delta S. Remember, there's that minus sign in between there. We are summing them up. We know the enthalpy term is positive and the entropy term is positive also. Now the overall T delta S term is going to be negative because of the negative sign in front of it. Okay? In order for this to work, we need to look at the enthalpy units and the entropy units. And you should see here that the enthalpy units are in kilojoules and the entropy units are in joules per Kelvin. And that's why that T delta S term is so crucial. Okay, it's at room temperature, so we do know the temperature at that 25 degrees Celsius. We're going to add 273 to that to get our 298 Kelvin. Okay, and then we need to make sure that our joules and kilojoules are in the same set of units. Typically, we take our joules and convert them into kilojoules and leave the enthalpy term alone with the kilojoules. Okay, and then therefore, after having the same set of units, then we can sum up the values. So that's one of the most important concepts here mathematically in solving this problem, is making sure that your units cancel. So we're going to plug in these values. I got 6.95 kilojoules for the enthalpy term. I got my 298.15 Kelvin, that's at 25 degrees Celsius. I got the 28.59 joules per Kelvin. You should see of the entropy term. You should see that the Kelvin terms now cancel out. Then I have a unit conversion going from joules to kilojoules by multiplying 1 kilojoule over 1,000 joules. Therefore, the joules terms cancel out and I'm left with kilojoules for that T delta S term. Now I have kilojoules there for the T delta S term in total, and I also have kilojoules for the enthalpy term. And so now I can sum up these two numbers. Okay, and here is my number. I have negative 1.57 kilojoules is the overall Gibbs free energy for this reaction. Now again, that numeric value is very important, don't get me wrong, but what's most important here is the sign of this value, and that it is negative. So we're going to ask ourselves, is this a spontaneous or a non-spontaneous reaction? And we're going to refer back to the sign of the Gibbs free energy. And since the Gibbs free energy term is negative, that means that this is a spontaneous and product-favored reaction. Okay, so you should understand that if you had ice on the counter at room temperature, it will spontaneously melt from the solid state to the liquid state. It will do a state change from the solid state to the liquid state. And that should make sense because of that negative sign for the Gibbs free energy. Okay, now what is the driving force for this reaction? You should see that the enthalpy, okay, is endothermic, and the entropy, okay, is positive and more disordered. Therefore, they're working in opposite directions here because they are of the same sign. So we got to figure out what is the overall driving force. What is pushing this reaction forward? Is it the enthalpy or is it the entropy term? So we got to look and figure out which term is larger. And so since they have separate different kinds of units, that is entropy is joules per Kelvin and enthalpy is kilojoules, we can't compare those values right there. But what is really easy to do is to look at the enthalpy and the entropy and then the overall Gibbs free energy. The overall Gibbs free energy is spontaneous and product favored. So which of the two, the enthalpy term or the entropy term, was product favored, i.e. going towards spontaneity? And since the enthalpy term being positive and the entropy term being positive, they are opposite, right, from each other. However, since the entropy term is larger than the enthalpy term, the driving force is entropy. Okay? This is validated by the fact that liquid water is more disordered than solid water, i.e. ice. Okay? That is, the enthalpy term is going reactant favored. It is in the endothermic process. And the entropy term is the product favored or spontaneous process. And since the Gibbs free energy is also spontaneous, we know that Gibbs free energy being spontaneous and the entropy term spontaneous, then we know that those two are going together, and of course the overall is spontaneous because the sign of the Gibbs free energy. Hopefully that video made sense for you. I got a crazy hat here for you. I love this hat. I got this hat from a colleague at my school. It's all about world peas. and hopefully we can attain world peace. In fact, she's making videos too. She's making videos in math. So you might want to check out The Cat Lady Teaches. So check out The Cat Lady Teaches, and you might see her videos on YouTube as well. Please subscribe to her and give her a thumbs up. So if you like this video, give it a thumbs up. Please subscribe to my YouTube channel. I would greatly appreciate that. And don't forget it. You got stickers and hats and t-shirts. All right, I'll see you next time. Have a fantastic day. Bye for now.